Hello, my name is Luis Armando Pérez and I will be giving a more complete explanation of the paper A Metric for Linear Symmetry-Based Disentanglement, which will be presented as a poster at NeurIPS 2020 workshop on differential geometry meets deep learning. Our work is motivated from the idea that disentanglement is important, but there's no agreed upon definition. However, Higgins et al. Attempts to provide a definition for linear symmetry-based disentanglement. This definition is based on modeling symmetries of the real world using group theory. Examples of those symmetries are 2D rotations, such as those shown here, for a windmill rotating and its blades. So, linear symmetry-based disentanglement considers that there's an encoding function h that takes all our data from a data space X into an embedding space Z. And this function needs to fulfill certain properties. One of them is the equivariance, and this means that it tries to capture properties of those transformations. A second property is linearity, which means that the transformations in the representation space must be simple. And third, it needs also that the representations and the transformations should be disentangled. We will now describe in more detail each of the properties for linear symmetry-based disentangled representations. The first property, the equivariance of encodings, means that the function h should be equivariant with respect to the actions on the data space X and on the embedding space Z. This means that if we first encode an image of the windmill into the space Z and we apply a transformation, it should be giving the same result as if we first apply the transformation in the data space and then we encode this image into the encoding space Z. The second property on the linearity of group actions on Z means that the transformations on the representation space Z should be actually linear. The third property on the disentanglement of group actions means that for several independent group actions, the encodings should provide a separation of the embedding space with respect to those transformations. If we now have two independent rotations, one for the windmill and another for its blades, then the encoding should, for example, encode information about each transformation in two separate two-dimensional spaces, as it is shown in this image. Even though that we have a definition, we still need to have a metric to quantify linear symmetry-based disentanglement. In this paper, we propose a metric to measure linear symmetry-based disentanglement. In order to evaluate the level of linear symmetry-based disentanglement of an encoding, we require a dataset which has all generated images from a single base point, x0, through group transformations. In particular, in our work, we have focused on combinations of SO2 rotations, as in the example of the windmill rotations. We also require that each of these data points has the associated group transformation that was used to generate each data point from the base point x0. From those data points, we can obtain the embeddings by encoding them with a function h in the space Z. We can evaluate the disentanglement of such embeddings obtained from the encoding h by using the metric that we propose. The metric proposed is expressed by the formula presented here, which measures the equivariance of the encoded data with respect to the best disentangled group representation in the embedding space Z that fits those encodings. We will explain in an intuitive way the process for the evaluation of the metric. If we apply the inverse action for an arbitrary group representation to each embedding, we would expect that if h is equivariant, all points should be concentrated around the base point embedding, that is h of x0. The highlighted term that we show here in the formula shows the average of the encoded data points location in the latent space, which should be close to the embeddings of x0. The equivariance of the encodings can be then calculated by measuring the distances of each transformed data point embedded in Z with respect to this average, as highlighted. The final metric value is obtained from the infimum with respect to all possible group representations for the group transformations that are disentangled. In this case, we show it with rho star, which has lower distances to the average of the data points encoded. In our paper, we present both qualitative and quantitative results, which correspond to the data generated from group transformations of rotations as shown here. We visualize these encodings into an enfolded torus, where we have encoded our data. We show the effects of using our metric into the encodings obtained with different degrees of linear symmetry-based disentanglement. You can see that when you have perfect disentanglement, on the left, our metric is actually 0. Whereas when the linear symmetry-based disentanglement is worse, you get higher values of the metric. So, this paper addresses the problem that we need a metric to quantify linear symmetry-based disentanglement. Now, we have provided a metric to quantify it. With this, I would like you to thank you for your attention and see you at the NeurIPS2020 workshop on differential geometry meets deep learning.